Hello my friends and welcome back to the Today Machine channel. The production process of steel billets and wire rods begins with the collection of scrap metal, followed by melting, refining, casting, rolling, and final inspection, ensuring that the end product meets the highest industry standards. Scrap collection and melting. The production process begins with the collection of steel scrap from various sources, including old car bodies, household appliances, demolition materials, and other industrial and consumer products. This scrap is meticulously sorted into different types, ensuring the proper mix for the desired steel grade. The scrap is then transported to a mini mill, where it undergoes recycling and transformation into new steel. At the heart of the mini mill is the electric arc furnace, EAF, where the scrap is melted down. The EAF is a 115-ton furnace that uses high amperage and low voltage to generate intense heat, reaching temperatures of up to 3,500 degrees Fahrenheit. The scrap is charged into the furnace through a continuous charging system, and the melting process begins. During this stage, carbon and various alloys are added to achieve the desired chemical composition of the steel. Oxygen is also injected into the furnace to enhance the melting process and achieve the necessary temperature. Refining and continuous casting. Once the scrap has melted into liquid steel, it is tapped from the furnace into a ladle, holding 78 tons of molten steel. The ladle is then moved to the ladle metallurgy furnace, LMF, where the steel's chemistry is refined and adjusted. During this process, additional alloys are added, and the molten steel is stirred with inert gas to ensure homogeneity. The LMF allows precise control over the steel's temperature and chemical composition, which is critical for producing high-quality billets and wire rods. The next stage is continuous casting, where the molten steel is poured from the ladle into a tundish, a reservoir that feeds the steel into the billet caster. The caster draws the steel downward through a series of support rolls while water sprays cool and solidify the metal. This process forms the steel into billets, long rectangular shapes that serve as the starting material for rolling into wire rods. Rolling mill operation. The billets, now solidified, are straightened and cut to length using oxygen torches. They are then assigned unique identification numbers for tracking and quality control. The billets are stored in an indoor yard, where they cool down before being transported to the rolling mill for further processing. In the rolling mill, the billets are reheated to approximately 1,150 degrees Celsius in a walking beam reheat furnace. This step ensures that the billets are uniformly heated throughout, preparing them for the reduction process. The reheated billets are then passed through the breakdown mill, where they are reduced in size and shaped into long, round bars. Shaping and finishing. After passing through the breakdown mill, the bars are directed to the roughing, pre-finishing, and finishings, where they undergo further reductions in diameter. The bars can pass through up to 24 sets of rolls, with each stage progressively reducing the cross-section and increasing the length of the bar. Throughout this process, the bars are cooled in enclosed water boxes to ensure the steel's internal structure is optimized according to customer specifications. The final shaping of the wire rod occurs in the reducing sizing mill, where the rod is given its precise diameter, ranging from 4.75 millimeters to 25.5 millimeters. Advanced instrumentation measures the rod's diameter and surface quality, ensuring it meets exact customer specifications. The wire rod then moves to the cooling stage, where it is shaped into coils by a rotating laying head. Inspection and quality control. After the cooling process, the coiled wire rod is collected and subjected to rigorous inspection. Each coil is checked for grade, diameter, ovality, surface defects, and mechanical properties. If required, the coil may also undergo tensile strength testing. The final coil is then trimmed, shaped, tested, compacted, weighed, and tagged according to industry standards. The company's investment in a 3,300-ton forge press, coupled with an ultrasonic test large bar inspection line, enables the production of large steel bars with superior center soundness. These bars, critical for demanding applications worldwide. The production process of sound center engineered steel bars begins with the arrival of an as-cast ingot at the rolling mill, where it is placed in a soaking pit for reheating. The ingot is heated to a consistent temperature, preparing it for the next critical step, the forge rolled process. This process, developed and refined by Timken Steel, is designed to meet the specific requirements of customers who demand high-performance materials. Once the ingot reaches the desired temperature, it is subjected to the immense pressure of the forge press, which generates 3,000 metric tons of force. This pressure is applied uniformly across the entire length of the ingot, compressing the hot metal and improving its internal structure. The forging process includes multiple passes, each contributing to the enhancement of the ingot's center soundness and strength. This step is crucial as it ensures that the final product has a uniform and robust core, essential for applications where material integrity is paramount. Following the forging process, the semi-finished product is transferred to the rolling mill. Here, the rolling process further refines the bar, improving its shape and size control. The result is a steel bar with consistent foot weight and precise size tolerances. The combination of the forge and roll processes ensures that the final product not only meets but often exceeds industry standards for strength and reliability. By offering large bars up to 16 inches in diameter with enhanced center soundness, the company is able to meet the stringent demands of industries that rely on high-performance steel. Cold wound springs are crucial components in various mechanical systems, offering resilience and flexibility in applications ranging from automotive suspensions to industrial machinery. Below is a detailed explanation of the process, emphasizing the importance of material selection, winding techniques, heat treatment, and quality control. Material selection. The first step in producing 2 inches bar springs is selecting the appropriate material. Typically, high-carbon steel, such as ASTM A228 or SAE 1070, is preferred due to its excellent tensile strength and fatigue resistance. For a 2 inches diameter spring, a high tensile wire with a diameter ranging from 1.75 to 2.25 is selected to ensure that the final spring will have the desired mechanical properties. The selected steel is often supplied in coil form, with a tensile strength between 250,000 psi to 300,000 psi. The material's hardness before the winding process typically falls between 45 to 50 HRC, Rockwell hardness, ensuring it can withstand the stress induced during the winding process. Winding process. The cold winding process involves shaping the spring wire around a mandrel without preheating the material. This is achieved using a CNC, computer numerical control, coiling machine that precisely controls the tension and pitch during winding. For a 2 inches bar spring, the following parameters are typical. Mandrel diameter, 1.8 to 1.9, slightly smaller than the final spring inner diameter. Pitch, typically between 0.2 to 0.5, depending on the required spring index. Coiling speed, 20 to 30 revolutions per minute, RPM, to maintain control over the material and prevent work hardening during winding. Spring index. The ratio of coil diameter to wire diameter is usually maintained between 6 and 10 for optimal performance. During the winding process, the CNC machine exerts controlled pressure to form the wire into the desired helical shape. Given the thickness of the 2 inches diameter wire, the machine's feed rate is carefully controlled to prevent excessive strain, which could lead to material fatigue or fractures. Heat treatment. After the cold winding process, the spring undergoes a stress relief heat treatment to remove any residual stresses induced during coiling. This is typically done in a furnace at a temperature between 350 degrees Fahrenheit to 450 degrees Fahrenheit, 177 degrees Celsius to 232 degrees Celsius, for about 30 to 60 minutes, depending on the material thickness and the specific application of the spring. This process helps stabilize the spring dimensions and enhances its load-bearing capacity by ensuring uniform internal structure. For a 2 inches bar spring, this step is crucial because any residual stress could lead to premature failure under load. Shot peening. To further enhance the fatigue life of the spring, shot peening is employed. This process involves bombarding the spring surface with small steel or ceramic beads at high velocity. The impact of the beads induces compressive stress on the spring's surface, which counteracts tensile stresses during operation and significantly reduces the risk of stress fractures. For a 2 inches bar spring, the shot size typically ranges from 0.04 to 0.08, and the peening intensity is maintained at a level of 6 to 8 almond intensity, ensuring thorough surface coverage. Final quality control. After the heat treatment and shot peening processes, the spring undergoes rigorous quality control checks. These checks include dimensional inspection, ensuring the spring's outer diameter, free length, and coil pitch meet the specified tolerances. For a 2 inches bar spring, tolerances are often within plus or minus 0.01 for diameter and plus or minus 0.05 for length. Load testing. The spring is subjected to a load test to confirm it can support the required load without significant deformation. For example, a 2 inches bar spring might be required to withstand a load of 10,000 pounds. As of 2023, the market size for the global spring manufacturing industry was valued at approximately $24 billion, with projections indicating a steady growth rate of 4.5% annually over the next 5 years. This growth is driven by the rising demand for lightweight, durable, and high-performance springs, especially in the automotive and aerospace sectors. The automotive industry is the largest consumer of springs, accounting for nearly 35% of the total demand. Springs are essential in suspension systems, engines, and braking systems, among other applications. The increasing production of electric vehicles, EVs, and the ongoing trend of vehicle lightweighting to improve fuel efficiency are expected to further boost demand in this sector. Regionally, Asia-Pacific dominates the global spring manufacturing industry, contributing more than 40% to the market share. China, Japan, and India are major players due to their extensive automotive and industrial manufacturing bases. North America and Europe follow, each holding around 25% and 20% of the market share, respectively. These regions are characterized by advanced manufacturing technologies and high demand from the aerospace and defense industries. The industry is also seeing innovations in materials and manufacturing processes, with a growing focus on sustainability. For instance, the adoption of advanced alloys and composite materials for spring production is increasing, as these materials offer better performance and longevity. Additionally, advancements in manufacturing technologies, such as computer numerical control, CNC, machining and additive manufacturing, are enhancing production efficiency and precision, further driving the growth of the global spring manufacturing industry. The manufacturing process of razor blades begins with stainless steel strips, which are first inspected for quality. Once approved, the steel strip enters a punching machine that stamps it into the desired razor blade shape. In the first stage of blade treatment, the blades undergo a four-step primary process. The first step is heating the blades in a furnace at temperatures exceeding 1000 degrees Celsius. This high-temperature treatment alters the blade's molecular structure, preparing it for the subsequent steps. The second step involves cryogenic cooling, where the blades are rapidly cooled to sub-zero temperatures. This step further enhances the metal's hardness and durability. The third step is reheating the blades to restore their flexibility, ensuring they are not too brittle. These thermal processes collectively harden the metal and give it the necessary strength and flexibility for cutting. For double-edge blades, the next step is branding. The blades move through a printing machine that applies the razor blade brand name onto each blade. In the second stage, the blades enter a grinding and polishing machine, which has 3 grinding stations: pre-grinding, fine grinding, and accurate grinding. This multi-step grinding process is essential for creating a super sharp cutting edge on the blade. After grinding, the blades go through a polishing machine to remove any fragments left from the grinding process. Following polishing, the blades are cut into their final shape by a cut-off machine and are thoroughly washed and dried to remove contaminants. In the third stage, the blades undergo special material coating. The first coating layer is typically a protective material, followed by a Teflon coating on the edge. The blades then undergo heat treatment to ensure that the chromium and Teflon coatings are properly fused to the blade edge, enhancing its durability. After coating, the blades are inspected under blue light to check for any edge defects. Quality control labs also test samples to ensure that each blade meets the required hardness and sharpness specifications. For double-edge blades, the final step is packaging. Each blade is individually wrapped in wax and colorful paper by an automatic packaging machine before being boxed by another auto packaging system, ready for distribution. If you have a knack for precision and manual dexterity, enjoy working independently, and take pride in hands-on work, then a career in saw and knife maintenance might be the perfect fit for you. This profession offers excellent job prospects and the opportunity to learn specialized skills in a unique workshop environment. Sharpening and tensioning saws. One of the most critical skills you will acquire is sharpening saws. This process involves using grinding machines to refine the cutting edges, ensuring that they are sharp enough to cut through materials efficiently. You will also learn how to tension saws, a technique used to ensure that the saw blade remains straight and does not bend or twist during use. Proper tensioning is vital for maintaining the accuracy and safety of the saw. Knife sharpening. Similar to saws, knives require regular sharpening to maintain their cutting performance. You will be trained to sharpen different types of knives, from those used in manufacturing to specialized cutting tools, ensuring they remain effective and safe to use. Detecting and correcting anomalies. An essential part of your training will be learning to identify and correct anomalies in saws and knives. This could include detecting irregularities in the blade surface, such as cracks, nicks, or warping, and knowing how to address these issues to prevent accidents and ensure the tool's longevity. Welding. Welding is another crucial skill you will learn. It is often required in the repair of saws, particularly when a blade breaks or becomes damaged. Mastering welding techniques will allow you to repair these tools, extending their usable life and reducing costs for businesses. Repairing and replacing saws. The ability to repair and replace saws is fundamental to the role. You will learn how to disassemble and reassemble saws, replace worn-out parts, and ensure that the saw operates as efficiently as possible. Saw and knife sharpener in a wood processing plant. You could work in a factory setting, maintaining the tools essential for wood cutting and processing. These industries rely heavily on sharp, well-maintained saws and knives to ensure production runs smoothly. Sharpener in a saw and knife manufacturing workshop. Another option is to work in a workshop where saws and knives are manufactured. Here, you'll ensure that new products meet the highest standards before they are shipped to customers. Self-employed sharpener. With the skills you've acquired, you might decide to start your own business, offering sharpening and repair services to local industries, workshops, and individual customers. Modern technological advances have significantly transformed the manufacturing of circular saw blades, enhancing their efficiency, durability, and cutting precision. The integration of advanced materials, sophisticated design processes, and state-of-the-art production techniques has enabled the production of circular saw blades that are not only more efficient but also last longer, providing better performance across various applications. Materials and coating technologies. One of the most significant advancements in circular saw blade manufacturing is the development of new materials and coating technologies. High-speed steel, HSS, and carbide-tipped blades have become industry standards due to their superior hardness and resistance to wear. For instance, carbide-tipped blades can maintain sharpness up to 10 times longer than traditional steel blades, significantly reducing downtime for resharpening. Furthermore, the use of advanced coatings such as titanium nitride, tin, or diamond-like carbon, DLC, has increased blade durability by reducing friction and heat generation during cutting. These coatings can extend blade life by up to 50%, making them more cost-effective in the long run. Precision manufacturing. The precision of circular saw blades has been enhanced through advancements in computer numerical control (CNC) machining. CNC machines can produce saw blades with tolerances as low as plus or minus 0.005 millimeters, ensuring consistent quality and performance. The ability to control every aspect of the manufacturing process, from the grinding of the teeth to the balancing of the blade, allows manufacturers to produce blades with exceptional accuracy. This level of precision is crucial in applications where even slight deviations can lead to poor cuts or material wastage. Innovations in tooth geometry. Tooth geometry plays a critical role in the cutting performance of circular saw blades. Modern manufacturing techniques have allowed for the development of specialized tooth designs tailored for specific materials and cutting conditions. For example, triple chip grind (TCG) tooth configurations are now commonly used for cutting hard materials like aluminum and non-ferrous metals. These designs help to minimize material deformation and reduce the risk of blade wear, leading to smoother cuts and longer blade life. Laser cutting and heat treatment. Laser cutting technology has revolutionized the production of circular saw blades by enabling more intricate designs and reducing material waste. Laser cut blades can have precisely cut expansion slots that reduce vibration during cutting, improving the blade's stability and extending its lifespan. Additionally, modern heat treatment processes have been refined to produce blades with a more uniform hardness distribution, enhancing their resistance to wear and fatigue. A high-quality circular saw blade can now achieve a Rockwell hardness of up to 62 HRC, making it suitable for cutting even the toughest materials. Environmental and economic benefits. The advancements in circular saw blade manufacturing also have environmental and economic benefits. The extended life of modern blades means fewer replacements, reducing material consumption and waste. Moreover, the increased efficiency of these blades results in lower energy consumption during operation, contributing to more sustainable manufacturing practices. The GC 2220 turning inserts are specifically designed for stainless steel machining, offering remarkable resistance to plastic deformation, which is crucial in maintaining tool integrity during demanding operations. This turning grade is particularly well suited for stable machining conditions, where consistent performance is essential. A key feature of the GC 2220 is the Enveo coating, which enhances wear resistance and extends tool life. The coating consists of tightly packed, unidirectional crystals that form a robust barrier between the cutting zone and the chip. This barrier significantly reduces the amount of heat generated at the cutting zone, leading to improved crater and flank wear resistance. As a result, machinists can expect longer and more predictable tool life, which is especially important when working with materials like austenitic and duplex stainless steel. The inserts perform exceptionally well in conditions ranging from continuous cutting to light interruptions, and they are optimized for use at average to high cutting speeds. Their design, combined with the high-performance substrate and precise post-treatment processes, makes them an excellent choice for ISO-M machining applications. For those in need of expert advice, the Steiner Metalworking Application Team offers assistance in selecting the right inserts for specific stainless steel machining requirements. They can also provide guidance on process improvements aimed at increasing yield rates and reducing costs, ensuring that operations are both efficient and economical. The Morn Fiber Laser Cutting Machine is a highly versatile tool used in various industries for cutting materials like carbon steel, stainless steel, and galvanized sheets. It operates by emitting a concentrated laser beam from a fiber laser source, which is directed through a lens to focus on the workpiece. This focused laser beam melts or vaporizes the material at the cutting point, creating a precise and clean cut. The machine's CNC, computer numerical control, system ensures accurate positioning and movement of the cutting head, allowing for intricate designs and complex shapes to be cut with high precision. Traditional swordsmithing in Pakistan is a centuries-old craft that has been passed down through generations, preserving the ancient techniques and artistry that have made Pakistani swords renowned worldwide. This artisanal practice, particularly prevalent in the regions of Wazirabad and Peshawar, continues to be a symbol of cultural heritage and pride, embodying the skills and dedication of the craftsmen who devote their lives to this demanding yet rewarding profession. The art of swordsmithing in Pakistan dates back to the Mughal era, when sword-making was not only a necessity for warfare but also a highly respected craft. The swords produced during this time were known for their superior quality, intricate designs, and exceptional sharpness. The Mughal Empire, which ruled over the Indian subcontinent from the 16th to the 19th century, heavily influenced the development of swordsmithing techniques that are still in use today. The process of crafting a traditional sword by hand is labor-intensive and requires a high level of skill and precision. It begins with selecting the appropriate steel, which is often sourced locally. The steel is heated in a forge to a temperature of around 1,200 to 1,300 degrees Celsius, 2,192 to 2,372 degrees Fahrenheit, at which point it becomes malleable enough to be hammered into shape. Swordsmiths use a variety of hammers, anvils, and tongs to meticulously shape the blade. The forging process can take several days, depending on the complexity of the sword's design. After the initial shaping, the blade is subjected to repeated cycles of heating and hammering, followed by careful cooling, to enhance its strength and flexibility. This process, known as tempering, ensures that the blade can withstand the rigors of combat while maintaining a sharp edge. One of the most distinctive features of Pakistani swords is the intricate patterning on the blade, often created using a technique called Damascus steel. This involves folding and welding multiple layers of steel together, creating a distinctive wavy pattern that is both beautiful and functional. A typical Damascus blade might have between 300 to 500 layers of steel, each contributing to the sword's unique appearance and durability. In Pakistan, swordsmithing is typically a family trade, with skills and knowledge passed down from father to son. Many of these craftsmen begin their training as young as 10 years old, spending years mastering the various techniques required to produce high-quality swords. By the time they reach adulthood, they are skilled artisans capable of crafting swords that are not only functional weapons but also works of art. There are an estimated 500 to 600 traditional swordsmiths still practicing in Pakistan today, with the majority of them based in Wazirabad, a city often referred to as the City of Cutlery. Despite the rise of modern manufacturing techniques, these artisans continue to rely on traditional methods, using hand tools and forges to create each blade. While the demand for traditional swords has declined due to the advent of modern weapons, there remains a niche market for these handcrafted items. Collectors and martial arts enthusiasts from around the world seek out Pakistani swords for their historical value and craftsmanship. A high-quality traditional sword can sell for anywhere between $300 to $2,000, depending on its design, materials, and the reputation of the swordsmith. In addition to their practical use, these swords hold significant cultural and symbolic meaning in Pakistan. They are often presented as gifts during important ceremonies and are seen as symbols of strength, honor, and heritage. The intricate designs and craftsmanship reflect the rich cultural history of the region, making each sword a unique representation of Pakistani artistry. Despite its rich history and cultural significance, the future of traditional swordsmithing in Pakistan is uncertain. The number of practicing swordsmiths is dwindling as younger generations turn to other professions, and the craft is increasingly being threatened by the availability of mass-produced, machine-made swords. However, there is hope that this ancient craft can be preserved. Initiatives to promote traditional crafts and the growing interest in handmade, artisanal products may provide the support needed to keep swordsmithing alive in Pakistan. By embracing modern marketing strategies and expanding their reach to global markets, Pakistani swordsmiths can continue to share their unique craftsmanship with the world.